Okay, this is the first time I've had you watch a video. What you do when you watch a video of a lecture is you use the pause key a lot. If I'm going too fast, pause it. If, for example, this is third period and I did the beginning of the notes, you might want to fast forward through it because I'm starting from the beginning. So multiplying probabilities. The occurrence of one of the events does not affect the probability of the second event occurring. These two would be called independent events. And the probability that two independent events, A and B, are independent of each other, the probability of A and B is equal to the probability of A times the probability of B. An example would be you toss a coin, heads or tails, you roll a die, and I'm assuming it's a six-sided fair die. Those are totally independent of each other. So, probability of tails and 3 would equal the probability of tails times the probability of getting a 3. You can either get heads or tails. So you'll get tails 1 out of 2 times. The probability of getting a 3, there's only one way to get a 3 out of 6 sides of the dice. 1 times 1 is 1. 2 times 6 is 12. 1/12 is your answer. If the occurrence of the first event does affect the second event occurring, the probability of it, then instead of independent, they are dependent events. An example would be I'm drawing a card from a deck of cards, and then I'm not replacing it, and then I'm drawing a second card. It's dependent on what the first card is. That's why it's dependent. So what is the probability of drawing an ace from a deck of cards and not replacing it, and then drawing a queen? So I want the probability of an ace times the probability of a queen. So what's the probability of drawing an ace? Well, there are 4 aces in a deck of cards, and there are 52 cards in a deck. Now assume that first card is an ace. I drew an ace. Now, I don't have 52 cards in my deck. I have 51 cards in my deck. So if I drew an ace the first time, how many queens are left in the deck? And 4 queens are left in the deck. I'm going to have you leave probabilities as fractions. So I would probably reduce this fraction before multiplying it all out. 4 goes into 52 13 times. So that fraction changes to 1/13. So now 1 times 4 is 4. And then 13 times 51. And if you don't know what 13 times 51 is, I think it's 663. But if you don't know what it is, pick up your calculator. 13 times 51 is 663. So 4 over 663. And you can just leave it as a fraction. The probability of event A occurring, given that event B already occurred, is called a conditional probability. And it's represented by this P for probability, B, and then a line, and A. And this is read as the probability of B given A. So that's the probability of B given A. So if two events A and B are dependent, the probability of A and B is the probability of A times the probability of B given A already occurred. So let's find some dependent. I have a bag of marbles, 12 red, 9 blue, 11 yellow, 8 green. 2 marbles are drawn sequentially, so you're going to draw one, not replace it, and then you're going to draw a second one. The probability of a red and a blue marble is equal to the probability of red times the probability of blue given red. And on your notes, I think you need to write that. I forgot to white it out. And that's using this. The probability of red and blue is equal to the probability of red times the probability of blue given a red. So A is red in this and B is blue. So how many red marbles are all together? There are 12 red marbles. Out of how many marbles? So if you add up your marbles, 12 and 8 is 20, and then here's another 20, so that's out of 40. And then reduce that. 4 goes into both of those. 4 goes into 12 3 times. 4 goes into 40 10 times. So now I have a marble. So I don't have 40 marbles anymore. I have 39 marbles. And there are 9 blue marbles. And I would like to reduce those fractions before I go on. So 3 goes into each of these. 3 goes into 9 3 times. 3 goes into 39 13 times. So the probability of red and blue would be the probability of red, which is 3/10, times the probability of blue given red, which is 3/13. 3 times 3 is 9. 10 times 13 is 130. Oops. Next one. If I take that probability of A and B is equal to probability of A times the probability of B given A, if I take that and solve for this, so I want this all alone, to get rid of that P of A, since it's attached by multiplication, I would divide each side by P of A, and they cancel there. And then I'd have the probability of B given A is equal to the probability of A and B divided by the probability of A. As long as the probability of A does not equal 0. Because if it did, that math would not work because it would be undefined. So at a restaurant, 25% of customers ordered chili. If 4% of the customers ordered chili and a not backed potato, a baked potato, find the probability that someone who orders chili also orders a baked, spell check didn't catch it because that's a word, baked potato. Okay? So the probability of a baked potato given chili. Baked potato given chili. Baked potatoes by B. Baked potatoes by B. Chili's my A. So it's the probability of chili and a baked potato over the probability of chili. So it said 25% of customers ordered chili, and 4% of the customers ordered chili and a baked potato. So 0.04 divided by 0.25 is 0.16. So the probability that someone who orders chili also orders the baked potato is 0.16 or 16%. A contingency table or two-way frequency table is often used to show the observed or relative frequencies of data from experiment classified according to two variables, with rows being one variable and columns being the other. You saw this yesterday in class. Yesterday in class, do you remember that table I made? I made a table with the type of car, SUV, and sedan. And then I did a color. I don't remember what it was called, maybe red, blue, and black. That table was a contingency table, or two-way frequency table. Okay? So there's an example of one. A drug company conducted an experiment to determine the effectiveness of a certain new drug. Test subjects were randomly assigned to one of two groups, a treatment group, which received the drug, a controlled group, which received a placebo instead of the drug. Results are shown. Okay, so yesterday when we did this, I added one more column and one more row. Do you remember what that was? It was the total. So you need to find the totals. okay? And sometimes what people do with these tables too, you don't have to, but what sometimes the people do is they divide everything by this total amount and make these all decimals. You don't have to, you can keep the numbers. Your book, I think, divided it out, but you don't need to. So the probability that your condition improves, that's why, given you were in the treatment group. Using that formula, it would be the probability of, it's the probability of a treatment and Y over the probability of treatment, okay? So, probability of treatment and yes, you improve. Can you see that there are 1,600 people that had, make it bigger, 1,600 people right here, 1,600 had a treatment and yes, it improved out of the 4,000? And can you see that 2,000 had the treatment out of 4,000? And if you remember your math from middle school, numerator divided by denominator is the same thing as your numerator times the reciprocal of your denominator. So you take this numerator, and then you take the reciprocal, meaning you flip it, of the denominator. So I'm not going to put this in my calculator yet, because look, those cancel out. And look here, 2 zeros cancel out there. So now I'm down to 16 over 20. Okay? And if I want it as a fraction, just keep reducing it. 8/10, which is 4/5, which is 80%. Now I want to find the probability that the subject was in the control group, C, given N does not improve. Okay? So if you do the same thing you just did here, probability, instead of T and Y now, it's C and N. C meaning control group, N meaning does not improve, over the probability of no improvement. So how many people were in the no improvement and the control group? 800 out of the 4,000. The probability of not improving is 1,200 out of 4,000. And again, 8,000 over 4,000 times 4,000 over 12,000. 4,000s cancel out. The 2 zeros cancel out. And now I'm at 8 over 12. 4 goes into that 2 times, which is 2/3, which is about 67%. And if you don't know it's 67%, 2 divided by 3 equals times 100 to get it to a percent. 66.7%. And I rounded just to 67%. Okay? Look online for homework.